Good morning, friends. We are here today to talk about the geometric mean and how it applies to similar triangles. So we're going to start off talking about the difference between arithmetic mean versus geometric mean. In the past, when you've learned about finding the mean or the average of two numbers, we've been talking about the arithmetic mean. That's where we add the numbers together. 8 plus 32 is 40. And then we divide by the number of numbers. 40 divided by 2 gives us 20. When we are talking about the geometric mean, instead of adding, we multiply the numbers. 8 times 32 is 256. And then instead of dividing by the number of numbers, we take the nth root of the product. So here we have two numbers, so we're going to take the square root of 256, which is 16. Let's look at how those numbers compare to our means compared to the numbers in our data set. So if we have 8, 20, and 32, that's the arithmetic mean. 8 plus 12 is 20. 20 plus 12 is 32. 20 is in the middle because we can take away 12 from it and add 12 to it, and we get our extremes, 8 and 32. But with the geometric mean, 8, 16, and 32, we have something a little different. 8 times 2 is 16. 16 times 2 is 32. So from the geometric mean, we can multiply by 2 to get the upper extreme. We can divide by 2 to get the lower extreme. So in general, with the geometric mean, you multiply all the numbers together, and then you take the nth root of that product, n being the number of numbers in the data set. So if you have 3 numbers in the data set, you take the cube root. If you have 10 numbers in the data set, you take the 10th root. But for our purposes today, we're just going to be looking at the geometric mean of 2 numbers. Now, when to use the geometric mean, this is from Investotopia. It's good to use when you have numbers that are in a series that are not independent of one another, numbers that are connected to each other. And it's used in business and finance when we're looking at percentages that are calculating growth. It's also used when we're looking at population growth. So when numbers are connected to each other and we're showing growth, that's when geometric mean is used outside of geometry class. But today we're just going to be looking at triangles. So we have this theorem, Theorem 7.5 in our book, that when you draw an altitude of a right triangle, it forms 2 smaller similar triangles. So in this triangle, ABC, we draw the altitude, CD, and that forms 3 similar triangles. The smaller triangle, triangle CDB, is going to be similar to the medium triangle, which is similar to the original large triangle. And we can prove this because in the smaller triangle, we have angle B, and in the original triangle, we have angle B. And in the smaller triangle, we have a right angle. In the larger triangle, we have a right angle. So we can prove that these 2 triangles are similar by angle. The medium triangle has angle A. The original triangle has angle A. The medium triangle has a right angle. The original triangle has a right angle. So the original and the medium triangle are similar by angle. And since the small and the medium triangle are both similar to the original triangle, we can say that they are also similar to each other. But we could go through a more rigorous proof if we wanted to. But for right now, we're just going to know that we have 3 similar triangles when we draw that altitude. Okay, we're going to identify the similar triangles in this diagram. So I'm going to draw our small triangle, our medium triangle, and our big original triangle. I'm going to put in our right angles. And we're going to start off by labeling those angles. So in the original triangle, the right angle is at angle T. In the medium, the right angle is at angle U. And in the small, the right angle is also at angle U. Now we're going to look at the short sides of each triangle. So in the small triangle, the short side is US. So let's label that, U to S. In the medium triangle, the short side is UT. So we're going to label UT. And in the original triangle, the short leg is TS, so we're going to label an S. Now we're going to fill in the third angle, the third vertex. So the small triangle is triangle SU and then T. The medium triangle is triangle TUR. And the original triangle is TSR. Now we can write our similarity statements. In the small triangle, I'm going to start on the left side in these drawings. TUS is similar to, in the medium triangle, RUT, which is similar in the original triangle to triangle RTS. When we're writing our similarity statements, remember that the letters need to be in the correct order, so we know which angles correspond to which angles, which side correspond to which sides. Now, when we're going through all of this, being able to pick apart the three triangles and redraw it is probably going to be your best strategy, but I'm going to show you some other ideas. Okay, identify the similar triangles, then find the value of x. So I'm going to draw my small triangle, my medium triangle, and my original triangle. I'm going to draw the angle H as my right angle of the small. In the medium, we also have angle H, and the big triangle, that's at G. And the short leg of the small triangle is EH. The short leg of the medium triangle is HG. The short leg of the original triangle is EG. I'm going to fill in the third vertex. So in the small, we have EHG. In the medium, we have HGF. And in the original triangle, we have GEF. Now I'm going to put in what we know. We know that EG is 3, so we can fill this in. But that's also the hypotenuse of the small triangle. We know that HG is X. HG is X. And we know GF is 4. And we know that the entire length of EF is 5. We'll see if we need that for now. Okay, we can set up our proportion. We're looking for X here. So we can say that X over 3, because the two sides correspond, is equal to, oh, that will not work. I made a mistake there. Let's go back. That will not work at all. Okay. So we also know, I didn't set this up before, that EF is 5, so I'm going to fill that in on the original triangle. And now we can set up our proportion. That was a great mistake. So I'm going to say X over 3, the short legs of the two triangles, is equal to 4 over 5, the hypotenuse of each of those triangles. We use our cross products and we get 5x equals 12. So x equals 12 over 5. Okay, let's look at our next example. Okay, geometric means. We have learned right at the beginning of this video that the geometric mean of two numbers a and b is the positive number x, such that a over x is equal to x over b. In this proportion, a and b, those two numbers we call the extremes. That's the high and the low of our data set. And the x and the x, that is our mean. And you'll hear it said that the product of the mean, x times x is x squared, is equal to the product of the extremes. A times b is ab. So x is equal to the square root of ab. Okay, how this relates. In this triangle here, we can say that the the distance between AD, we can call that A, and the distance between DB, we can call that B, and we can call the altitude X. The longer leg of the medium triangle A over the short leg of the medium triangle X is equal to the long leg of the small triangle X over the shorter leg of the small triangle B. A over X is equal to X over B. And in computing that, X is the geometric mean of A and B. Okay, now we can pause this video and we can write out all of these different proportions involving the geometric mean, but I think it's better to redraw the triangles and try to figure out the corresponding parts rather than trying to memorize all of these different proportions. And you can if you want, but I think it's good to redraw the triangles and look for the corresponding parts. Okay, find the value of X, write your answer in simplest form. So let's look at what we have. In the small triangle, we have this small triangle here. We have the hypotenuse and we have the short leg. In the original triangle, we also have the short leg and we have the hypotenuse. So we can, actually I said let's redraw the triangles, so let's redraw the triangles. So in the small one, we have S, R, Q. In the original triangle, we have Q, P, and R. RS is 3, RQ is Y. In the original triangle, RP is 9, RQ is Y. So we can say that the hypotenuse of the larger triangle, 9, over the short leg of the larger triangle, Y, is equal to the hypotenuse of the small triangle, Y, over the short leg of the small triangle, 3. And there's your geometric mean. The product of the means is equal to the product of the extremes. So y squared is equal to 27. So y is equal to the positive square root of 27. And it wants our answer in simplest radical form. So y is equal to square root 3 times 9. Y is equal to 3 root 3. And let's go back to our original triangle and see how this proportion looks visually. So we said 9 over y is equal to y over 3. 9 over y is equal to y over 3. Okay, these are two of the common ways that we see the geometric mean. The first one we kind of already looked at. The short leg of the small triangle over the altitude is equal to the altitude over the, oh, sorry, I messed that up again. The short leg of the small triangle is equal to the medium leg, the longer leg of the small triangle, and we can say that it's equal to the short leg of the medium triangle all over the longer leg of the medium triangle. And it kind of forms this shape like you would see on a little heartbeat machine in a hospital. I'm sure it has a more exact name. dB over CD is equal to CD over AD. We can also say the hypotenuse of the original triangle over the short leg of the original triangle is equal to the hypotenuse of the smaller triangle all over the short leg of the small triangle. But once again, we're just looking for the corresponding parts of the three triangles because all three triangles are similar. When in doubt, take the triangles apart, redraw them, figure out all the corresponding parts, And you should be able to find some great success with the geometric mean and triangles. Please let me know if you have any questions. Thanks.